Hi, everybody. This is Dr. Nigro with a Chem Calculation screencast. This one's going to focus on the technique of mass spectrometry. I've already looked at general spectroscopy, including the techniques of IR spectroscopy, UV-Vis spectroscopy, and PES spectroscopy. Mass spectrometry is another technique that comes up quite a bit in AP chemistry, and it's lumped in with these other techniques because it's an analytical technique, but it is not a spectroscopic technique. Spectroscopic techniques deal with the interaction between radiation or light and matter, and mass spec is not one of those techniques. It does not have anything to do with irradiating a sample with light. It's very different. All right, so the first thing to keep in mind is that mass spec is a non-light based analytical technique. All right, so you're going to see that the setup looks very different than what we have looked at before. All right, so first of all, let's talk about what you can use it for. So it's used in our case to determine the masses and relative abundances of various isotopes of an element. All right. So we tend to introduce this technique when we're talking about atomic structure, and in particular when we're identifying isotopes and how the mass and percent abundance of those isotopes can be utilized to determine the average atomic mass that we see on the periodic table. Well, the determination of those percent abundances and those masses came from this technique, mass spectrometry. All right. So it's important to go back and understand how we got all those numbers versus just understanding the mathematical portions of it. Now, mass spectrometry is not limited to elemental analysis. It can also be utilized to look at molecules, but that again is going to be outside of the purview of AP chemistry. But if you take organic chemistry, you are going to learn a whole lot about that. It's like a puzzle. It's one of my favorite things. All right, so let's talk about the setup because as you can see, it looks very different than our general setup for a spectroscopic or light-based technique. All right, first up, our sample. For us, these are going to be elemental samples. All right, and they have to be in the gaseous state. All right, so in other words, they need to be vaporized first. So there's going to be very high temperatures involved. All right, and that vaporized substance is then injected into this next chamber, which is called the ionization chamber. All right, so there's going to be some sort of current that's produced in this top part. All right, and that current is going to produce some high energy electrons. All right, and those electrons have enough energy to knock off a valence electron from your sample. All right. So it's different from photo PES spectroscopy. We're not using light to do this. We're using another piece of matter. So we're using an electron that is the same mass as one of your valence electrons, but it's moving at a high rate of speed and therefore has enough energy when it collides with a valence electron to displace that valence electron. And what that does is it takes our sample from being neutral to having a +1 charge. All right, so it ionizes, hence the ionization chamber, our sample. Now we are going to focus only on +1 charges. We're not going to deal with samples where 2 electrons have been knocked off or 3 electrons. It can get very complicated, but for us, single electron is removed, forming +1 ions. All right, now in the acceleration chamber, these positive ions are propelled down the chamber from a positive plate to a negative plate. They are repelled by the positive plate, attracted to the negative plate. All right. purpose here is to increase oops, and equalize the speed of all our ions in that sample. All right. So by time they're leaving that acceleration chamber, they should all be moving at the same speed. That is the goal. All right. Some of them may initially come into that chamber moving slower. By time they exit that chamber, everything is moving at the same speed. And what that does for us is it takes speed out as a variable in the experiment if everything's moving at the same speed. So the speed will be the same, the charge will be the same. The only difference amongst the particles once they exit the acceleration chamber should be their mass, which is perfect. All right, so up next is the deflection chamber, and this is comprised of magnetic plates. All right, so it's capable of building a magnetic field, and this is the most important portion of the experiment. Now, they're all important, but this is particularly important. All right, so these charged ions are bent around the curve by these magnets. All right, the degree of bend depends on mass of ion and strength of magnetic field. All right. So the best analogy I've seen for this is think about the magnetic field as like wind blowing across this tube. So the field is going this way. All right. If you have a particle that enters that chamber that is heavy, right, then that wind is not going to have as much of an effect on that particle's trajectory as something that is lighter. All right, so depending on the strength of that wind, it's going to bend the particles based on their mass. All right, so again, if something comes in that's heavy, it's going to need a very strong magnetic field to make that bend. If something comes into that tube that's lighter, it will not need as much of a strength of field. And the field is changing throughout the experiment. It is scanning back and forth over a distinct set of magnetic field strengths. So you're getting constantly changing bending for these different particles based on their mass. All right. So as they come through, if they get bent correctly, they're going to come and they are going to hit the detection plate. All right. So the detection plate lights up. Well, that's not really right. I mean, basically, electrical current gets produced if a charged entity hits it. All right. So when the ion hits the plate, all right, and based on the magnet strength of the magnetic field, it can calculate what the mass of that particle is. All right. So what we get are peaks at a particular mass, and intensity equals abundance. All right. So again, if you have the field set at a low strength field, you're going to get a lot of the lighter particles hitting that plate. As you increase the strength of that field to higher magnetic field strength, you're going to get your heavier particles hitting the plate. If the field does not have enough strength for the particle to make the bend, or too much and it basically crashes out over here, then you won't hit the plate. It doesn't get registered. All right. But as I said, the experiment runs with a scanning of that field. It's not just one set magnetic field strength. It's scanning a variety of values. All right, so what does the spectrum look like? It looks like something like what I've showed here, all right, where we've got the natural abundance here, all right, and that percent abundance well, actually, let me back up. Let me start over. All right, let's talk about what the peaks are first. So the peak on the spectrum tells us that an ion with that mass to charge ratio hit the detector. All right, now this idea of mass to charge, for us, it's mass per +1 for the charge. So it's just the mass. All right, if you had a technique that was provided or was forming +2 ions, then you would need to divide the mass values by 2. If they were forming +3 ions, you have to divide by 3. But for our purposes, it's always going to be a +1 charge. So we don't need to worry about that. All right, the height of the peak is proportional to the number of ions with that mass, which for us is the percent abundance. All right. So you can use a spectrum to ID an element or calculate the average atomic mass, which I'm going to abbreviate for the rest of this screencast as AMM because that's a lot to write over and over again. All right, if you want to ID that element, use your most abundant peak as a starting point and your periodic table. All right, so this particular spectrum is for magnesium. All right, so you can see it has 3 isotopes: magnesium 24, magnesium 25, and magnesium 26. All right, let's say I didn't know it was magnesium, it was just X. All right, I know that its most abundant isotope is around a mass of 24. So I'm going to start by looking for elements that have average atomic masses around that value. All right. I also know it has 2 additional isotopes that have higher atomic masses. So that means the average atomic mass for this element should be slightly higher than 24. It's not going to be a lot higher because I don't have a lot of abundance when it comes to those 2 other isotopes, but it will be higher. All right. So then I go look for an element that's around 24, but slightly higher. And if I do that, I'm going to land on magnesium. All right. So that's how you can utilize the chart to determine not chart, spectrum to determine what element it is. All right. So we're going to work a couple problems just so you can see what these look like. All right. So for this first one, we have a mass spectrum for a sample of lithium. All right. So we've got the relative intensity, which is our percent abundance, or the relative intensity one to another. And then we have the mass charge ratio. And remember, for us, this is going to be mass to a +1 charge. So we don't need to change the mass values. All right. So first up, how many isotopes of lithium exist? So according to this, I have 2 peaks. So there are 2 isotopes. All right. Label each peak with the nucleotide symbol for each isotope. All right. So remember, that's the atomic notation. So lithium, all right, this has a mass of 6. All right. And lithium has 3 protons. So that'd be my nuclide symbol. And then for this one, this is lithium again, mass number of 7, still 3 protons. All right. So those are my 2 symbols. All right. Without performing any calculations, predict the approximate atomic mass for lithium. All right. So I'm going to look. It is clearly going to be close to 7. All right. But I do have an isotope with a slightly lower mass. So I'm going to predict average atomic mass around, oops, not 7, 6.9 AMUs. Isotope Li7 is the most abundant, but Li-6 will a slight decrease in calculating the average atomic mass. All right, now it says use the relative intensity of each peak to calculate the percent abundance. So we're going to start with that to calculate percent abundance. All right, so let's start with the percent abundance and we'll do lithium 7 first. All right, so the relative intensity, the peak for lithium 7 is 100, and then the total is 100 plus 8 is 108. All right, so 108 times 100%. So the percent abundance for this is 92.6%. All right, then we repeat, but this time we look at lithium 6. Same general idea, except 8 for the relative intensity of that peak versus the total times 100, and we get 7.4% for this one, which makes sense. The two should add up to a total abundance of 100. All right, now calculate the average atomic mass of the element. So remember, this is a weighted average calculation, which means you need the abundance and the mass of each isotope, multiply the percent abundance times its mass, and then add all of those together. All right, so the average atomic mass for lithium is going to be equal to our mass number of 7 times 0.926, that's my percent abundance divided by 100, plus a mass of 6 times 0.074, which is the percent abundance for my other lithium isotope. And once I figure out my math, I get 6.93 AMUs, which is pretty close to my estimate. And if I go look at the periodic table, it is also pretty close to what is on the periodic table. All right. So the periodic table is always a way to check your answers for these problems. All right. Now, you still have to show your work. You can't just write it down based off the periodic table, but it should be a way to check what you're doing. All right. The mass spectrum of an average sample of an element is shown to the right. Identify the element and explain your reasoning. All right. So the first up, I have 4 isotopes of element X. All right. Of those 4 isotopes, the one with a mass of 90 is the most abundant. All right, so I'm going to start there. All right. Other 3 isotopes have higher masses. All right, so my first is going to look slightly above 90 AMU. All right, but I need to keep it less than 94 AMU. There's no way the mass could be up here. All right, it doesn't have enough mass. It's limited between 90 and 94 because those are the limits of our isotopes. All right, now my general guess is it's going to be it's probably going to be close to 92. All right, it's going to kind of depend on where we end up. All right, so if I go look at the periodic table, all right, the element most likely is going to be, so element's likely to be, I would guess zirconium. All right. It has an average atomic mass of 91.224 AMU, which seems reasonable, right? Because I've got some at 91, some at 92, and then some up at 94, but the majority is 90. So it's going to pull it closer to 90. All right. But I got to give myself a little bit of wiggle room. All right. Another option would be niobium, which has an average atomic mass of 92.91 AMU. But I think I would need more abundance in the isotopes above 90 AMU for that to happen. All right, so this would be my estimate. I would probably go with zirconium here. Now, what if I wanted to be absolutely sure? All right, so then I use math. All right, so your other option, and you can use this as part of your explanation. All right, you can calculate the average atomic mass of X. All right, so if I look at my chart, I've got a mass of 90. Now I come over, it's probably right about there. So I'm going to go with about 52%. So that's 0.52. And then I've got a mass number of 91. All right, if I look, all right, I'm going to say that that's probably around 12%. All right, a mass number of 92. All right, that's probably around 19%. And then my last one, my mass number of 94, that's really close, a little less than what I just did. So probably 0.17%. All right, so these are my abundances and my mass numbers based on my chart. And if I calculate that out, I get an average atomic mass of 91.18 AMU, which is much closer to zirconium. So my thinking above was correct. All right. So again, this is a way to determine the identity of an unknown element using its mass spectrum and logic. And then you can also utilize the mathematical application. That's the other way to do it. All right. Now, in conclusion, just remember mass spectrometry is not a spectroscopic technique. It's not light based. Right. Instead, it produces ions of your sample. Those ions are then accelerated to the same speed. And then, based on the strength of a magnetic field, either bend around a curve or do not. All right. If they bend around the curve and they hit the detector, they are registered for a specific mass. And the number of ions of that mass that hit the detector give the intensity or the abundance of that particular mass within that sample. From there, you build the spectrum, and from there, you can determine the average atomic mass or identify the element. Okay?